Image moteur Vulcain. Image confirmée.
누추하네.
Salut, service.
여보세요? Hola. Guro.
สวัสดี
Bonjour.
Sugashi doko arigato.
Welcome to the Rosetta Mission webcast. My name is Isabel Hawkins, and I'm an astronomer and senior scientist here at the Exploratorium. We're here to give you an update on the latest in the Rosetta Mission, which will do an unprecedented soft landing on a comet next week. And we're very excited to bring you the latest updates. And we have a special treat for today's webcast. Where we have invited the NASA senior scientist, Dr. Claudia Alexander, to join us from the Jet Propulsion Laboratory in Pasadena. And she's going to give you the latest news on what's going on and all the excitement of getting this very, very difficult feat to actually soft land a probe onto the comet. That's going to happen only in 6 days. So on November 12th, you have to be tuned, 7:30 in the morning, set your alarms, and the beautiful Philae module will land on the comet. So basically, what are we talking about? Let me just give you a little bit of a background on the Rosetta mission and what has been going on so that you have some context for the amazing event of next week. Here we see an image of a simulation of the orbit of the Rosetta mission. You see the solar panels up on top of the comet. You see the nucleus of the comet and the coma already flowing, starting to form a tail as the comet goes from its frozen state away from the sun, and on its orbit it starts to near the sun and warm up. And when it warms up, it starts to glow, it starts to release gas and dust, which makes comets so beautiful. So we're talking about this specific comet that has kind of a difficult double Russian name. So 67P is easy, but Churyumov, Gerasimenko is the Russian names of this comet, named after the two people who actually discovered it. So here's actually a juxtaposition of an actual image of the comet with the Rosetta Mission spacecraft that you see with the big solar panels, the larger instrument that we see here on the screen. And in between the comet and the Rosetta spacecraft, we see this beautiful little cube. It's almost like a little small satellite of sorts. And that is the Philae lander that will actually touch down softly on the comet, and hopefully everything will be just great so that we can get some unprecedented science done, because we have never been able to put a spacecraft on orbit around a comet, and in addition to that, we have never been able to soft land a module to be able to do some long-term studies and research on the composition of the comet, what it's made out of, what are the chemical elements that are part of the comet, which are actually the types of elements that we believe were present during the time when our solar system formed about 5 billion years ago. So here we see a movie of what it has taken for Rosetta to actually reach Comet 67P. It took 10 years, a 10-year travel, because the comet is traveling at 32,000 miles per hour. That is incredibly fast. We do not have rockets fast enough to just send it straight to the comet. So what's happened is that the spacecraft went through several slingshot events, getting assisted by the gravity of the Earth and by the gravity of Mars to be able to reach the kind of velocity that's needed to be able to get it this close. So here's an image that was taken on September 12th of Comet 67P. And what you see in here that is quite different from what the scientists expected. And I'm sure that Claudia will tell us a little bit more about the surprises that Rosetta has been able to uncover so far. But what we see here is that the comet is not your typical kind of roundish shape that was expected, but instead it kind of has two lobes, a major lobe and a minor lobe, or in lay terms, it looks like a rubber ducky. So basically, this is what the scientists are talking about, the head of the duck, the body of the duck. But what's interesting is that you might have different composition on the top lobe from the bottom lobe. Scientists don't know, was this middle part eroded away, or was this the result of a collision of two independent bodies? So is this a double comet? So the kinds of measurements that Rosetta and Philae are going to do will uncover some of those mysteries. And in particular, comets are almost like a time capsule that has preserved the composition of our early solar system. So if we want to know, how did the planets get here? How did they form? From that original chaotic solar nebula. How do we end up from that nebula to planets and people and poodles and pond scum and rubber duckies? So the idea is to really use this very specialized instrumentation from Rosetta and Philae to try and give us an insight into those very important questions. Let's see. Let's go to the next slide. And I think that this is one of everybody's favorite pictures, which is a selfie taken by Rosetta with the comet. So this is an actual photograph, and it's just fabulous. You can see the actual comet in the background, the two lobes, the ducky's kind of upside down at that moment, and you see the solar panel there. So to give you an idea of what we're talking about in terms of the comet, this morning I made a model of a comet. So here we are. Okay, I'm going to just take it out so that you can see it. And I'm wearing my gloves because this is primarily dry ice, frozen carbon dioxide. Here's a little bit of it. And you can see that carbon dioxide has an amazing property which simulates the behavior of some of the gases on the comet, which is sublimation, which is basically the state of matter that goes directly from a solid to a gas. So comets do not evaporate, they sublimate. And also comets are very, very dark. So the expectation is that the surface of the comet is very dark. And that's what we see and what we know of them. And that also that they have a lot of icy material. They are low density, they're porous, and it kind of looks like what we've seen on the actual images of the comet, and that's kind of exciting. So let's go to the next image. And then I want to bring you back to the Earth. So now we've seen the images of the comet from the spacecraft, beautiful high resolution, all of that detail. And now we're seeing an image of the comet as seen from Earth. It is much more distant, of course. And so that's something that it is the advantage of having spacecraft actually travel to these icy bodies, is that we get these unprecedented information and unprecedented views. But also what is exciting about comets, that if they do come near the Earth as they go around the sun, sometimes we will see spectacular views. Like, for example, Comet Magnat on 2007 gave us an amazing display of its tail as it entered the inner solar system and it got close to the sun. We don't expect that we'll be able to see Comet 67P in this configuration from the Earth, but what's amazing is that that spacecraft, Rosetta, will actually follow the comet as it comes into the inner solar system. It will continue to orbit. So in addition to Philae landing there and staying there hopefully for about 30 days doing all the experiments, we're going to have the Rosetta mission travel along with the comet around the sun and give us incredible views and incredible information. So here's a video, a simulation of what a comet really behaves like. So we talked about being icy bodies that orbit the solar system very, very far away from the Earth. And they are actually the remnants of an original state of the solar nebula, the solar system early stages. As that comet enters the inner part of the solar system, the sunlight and the solar wind, the particles of the sun, will actually heat up the comet, start to melt it. And then we see two types of material that will start to leave the comet. One is dust, and the others will be ions and gas, and up to the point that it will form a beautiful tail. So here it is. It's an actual image of our comet. Let me bring up my rubber ducky again. I think it's probably this way. So we have gas coming out of here in the middle. That's the image that we saw before, and so between the two lobes. So there is activity already on the comet, and this is actually of great concern to the scientists who are planning the Philae landing, because that could create some risk. I've heard it say it's almost like they're trying to predict what the weather will be like on the comet on the day of the landing next week on November 12th at 7:35 in the morning Pacific time. So that's one of the concerns. But basically, what is a comet made of? We have what makes it dark is the presence of interstellar dust particles. And when I'm saying dust, I'm talking about dust, because the material that makes up interstellar dust is the same material that makes the dust in your backyard. Talking about carbon, some minerals, iron, etc. So, because remember, the basic building blocks of the universe is what we share here on Earth as the basic building blocks of the planet and everything on it. And so the comet is kind of a reflection of what the early stages of the solar system were like. And so we have this combination of interstellar particles, and we also have some gases, for example, some carbon dioxide, some carbon monoxide, some water, some ammonia. And we will have some organics also, some of the material that the center of the Earth is made out of, diamond, graphite. These are the kinds of things that are expected to be found right here on the comet. So what's kind of cool is that one of the main ingredients of comet is water. And when you kind of bring my little comet here alive, we can see the sublimation occurring. So you have some jets and some porous material there. And if I do a little bit of hammering, you can see that the sublimation is pretty exciting. And here's some other parts of the comet. My little rubber ducky fell off, but I'm going to put it on if I can get it unstuck right here. But I was trying to make a rubber ducky. Here we go. It's kind of a little fatter one, but that's kind of our comet. And then we'll ask Claudia later on to really help us understand the kinds of experiments that are going to be done once the Philae lander touches down. Another really interesting thing about comets is that it's starting to sweat. So one analogy is that you have this comet sweating 2 cups of water each second. So you have 1 cup of water and another cup of water. So the comet is starting to shed its precious water as it gets close to the sun. So that's kind of cool. So I'm just going to give it back to it. But basically, water is a major ingredient. So that's one key message that I want you to take away with you, is that a comet has a great deal of water in it. As a matter of fact, some scientists believe that the water on Earth could have come from billions of comets that hit the Earth during the early stages of the solar system formation. So these are really amazing questions that we're talking about that hopefully the Rosetta Mission and Philae can help us answer. So let's talk a little bit about size. What are we saying here? Well, the comet is about 4 kilometers at its greatest diameter. That's about the length of Central Park. So it's not a very large comet, but it's large enough for a beautiful lander to hopefully touch down very safely next week. Just as a comparison, you have right here on the slide the comet kind of embedded inside the size of various buildings around the Earth and various mountains. And you can see it's about the size of the volcano Mount Fuji. One of the neat things that Rosetta has done is that it took a global map, made a big picture all around all the regions around the comet, to be able to understand what the composition is and to identify some potential landing sites. And what they have found is that the comet is the surface is primarily covered by dust. That's the inference when they did some temperature measurements of the comet. And that, again, could create some issues in terms of the landing, because if there's a lot of dust in the area and it's actually a soft surface, there are issues about whether it'll sink or whether they can anchor it safely enough, et cetera, because you're talking about a body that is small, so it doesn't have as much gravity as the Earth. So here's a simulation of what Rosetta did to be able to do a global map of the surface of the comet, to be able to ascertain some potential regions where Philae, the module, the lander, could actually touch down safely. So that was one of the main tasks of Rosetta, the mother mission, is to actually be able to make this map. And as a result of that investigation, the scientists came up with 5 potential landing sites. And we will ask Claudia to actually help us understand some of the criteria that we're putting question to figure out, okay, you know, what is a good spot for a lander? Because if you look at the shape of this comet, is actually quite irregular, and there are a lot of craters. There's a lot of areas in which it looks like there's even landslides. There are areas that have steep slopes. There are huge boulders the size of houses. Some of this entire webcast studio. And so how do you maneuver a lander which basically is going to be dropped from the spacecraft from an altitude of 22 kilometers and is going to just go? There's no way to maneuver it. The only stability that it has is a gyroscope, so to make sure that the feet land down. Other than that, we really don't know you know, where exactly it's going to go. The area that they have defined is about 1 city square block. It's about 1,000 meters on the side. That's the square, the landing area size. Within that, there's kind of an error of about 200 by 400 meter oval. That's kind of the error that the scientists and the engineers don't know exactly where on that comet that spacecraft is going to land. And so before we go to Claudia, let me just give you an idea of the kinds of instruments that Philae has and the kinds of things that might happen. And just so that you remember some of the questions that you might want to ask Claudia, I'm just going to kind of demonstrate the key instruments that are going to operate once Philae lands on the comet. So here's our model comet. And one of the things that is going to happen is when the Philae lands, it has 3 legs. So those 3 legs are going to touch down on the comet, and each leg has like a little tiny drill. So a little drill is going to anchor itself down. And there's also sensors on those feet. Like there's like seismometers to sense, you know, any kind of seismic activity on the comet. In addition to that, they have a drill. So a drill to drill down into the comet, and then when they take the drill out, they also have a scooper. This is obviously not to scale. A little scooper is going to come up, take a little bit of the comet, and put it in different parts of the Philae lander, which are little ovens. And those little ovens are there so that they can make the material volatile and they can study the composition of the various areas in which they're going to sample. And you might say, well, but if it just lands like that and the drill is going down, that's the only place that it's going to drill. But, you know, scientists and engineers are really smart, and so they figured out that they're going to make the whole Philae spacecraft rotate 360 degrees so that they can actually drill on different parts. That's pretty cool. So another thing that it's going to do, they're going to have a thermometer. All right, here we go. So they're going to have a thermometer, and they're going to hammer the thermometer down tung, 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 into the comet, and so that we can actually take the comet's temperature at various places. So that's another instrument. That's really cool. And another thing that they're going to do is they have a hammer. They're going to hammer into the comet, and that's going to give us some information on the mechanical and electrical qualities of the surface. And the other thing that they're going to do, which I think is just the coolest thing, they're going to take, I think 7 cameras. We're going to ask Claudia to give us the details, but I think it's 7 cameras that are going to take panoramas of the comet. And I'm just going to take a selfie with my comet and you, and we'll put it out. There we go. Okay, everybody. Yay, say cheese, wave at the Exploratorium. Yay, everybody wave. Woo! Okay, done. Selfie. hopefully we'll get other beautiful imagery, but it's going to be high-resolution panoramas of this entire view of the comet, including some of the horizon. So it's going to be just beautiful. I mean, can you imagine the excitement of these scientists that have waited for 10 years, and from the time when they actually put in their proposal, more than 20 years to actually get some of the data and be able to understand the origins of our solar system. So with that, I think we're going to go to Claudia right now and going to get her involved so we can tell us some of the answers. And Claudia is an amazing scientist. She actually went undergraduate in Berkeley here, then got her master's degree at UCLA, where I got my doctorate, so we got that in common. And then she went on to get her PhD at the University of Michigan. She's been working for NASA for many, many years, and she was project scientist for Galileo, the mission to Jupiter, and many other important NASA missions. But right now, she is the NASA project scientist for the entire United States for the Rosetta Mission. Let's welcome Claudia. Hey, Claudia, thank you. She's taking time from her incredibly busy schedule to be with us today. So welcome. How are you feeling?
Thank you. Thank you very much. I'm hungry. It's dinner time.
Me too. Let's eat some Comet. We got some ammonia and molasses hanging around here somewhere. Anyway, how are you feeling about the mission? Are you excited? Are you confident?
I mean, you know, when you work on a mission for this long, you can't imagine, you know, you work away and this moment is far off in the distant, my boss used to call it the sunlit uplands, right? Something that's so beyond the horizon that you think of it as a fantasy, you know, oh, one day we're going to land on the comet, and you actually, it's hard to imagine that you'll actually get there and you'll actually be doing this. And so I'm having this sort of amazing transition from fantasy land of, yeah, one day we're going to land on the comet, to actually, you know, like this is next week, okay? And I'm going to fly out there on Saturday, and we're going to be, you know, sweating and, you know, biting our fingernails watching this actually happen. It's a amazing time in your career. Anyone who's worked on space missions, it feels like an amazing thing to finally be there.
That's amazing. I have heard you say that comets are travelers in space and in time. Can you tell us a little bit more about that, and what are the main scientific questions that you hope to answer?
Yeah, comets got kicked out of the solar system really early on, and it's not clear exactly when. Maybe it was the first few million years, maybe it was the first few 100 million years, but sometime the solar system was forming, there was a lot of dynamics. We think that some of the major planets were moving back and forth, and in the cataclysm of two of the major giant planets switching places in their transition, there was a huge scattering event, and the comets were completely evacuated out of the solar system and put into a time capsule, put into a lockbox in the deep realms of outer space. One of the comet homes is called the Oort cloud, which is 100 million AU from the almost to the next star.
Wow.
That's how far away this disk is, where the comet, the long period comets have their home. And then the short period comets, we think, have their home in the Kuiper belt, which again is a very long way away. And it would be almost impossible for us to get there.
So that's why they're calling them icy bodies, basically. You call them icy bodies because they come from the very outer reaches of the solar system. And what kind of information do you think Philae, actually the landers, since we're so excited about this next phase, what do you think Philae will uncover? What are your hopes?
Well, you know, we really don't know. When you look at those pictures, you see something that looks straightforward. Your eyes tell you, oh, there's a landslide. Oh, there's a quicksand bog right there. There's a sand dunes and sand and landslides. But this is a really, really undense, ephemeral kind of body. We think that what it looks like to your eyes and what your eyes tell you about the geology is probably completely wrong. So the first thing that when we land on this thing, Is it going to be like talcum powder? Are we going to sink down like a half a meter?
That's the idea.
You know, we really need to have some ground truth that trains our intuition so that when we look at a picture, we actually understand what that material is.
So are you worried about the landing? Are you worried that, you know, are we going to soft land? Are we going to tumble? What's going to happen there?
Yeah, I'm worried.
You're worried. Oh my gosh.
I'm really worried, and I think everyone should understand that this is a hugely risky landing.
Unprecedented.
And we had to do, with this mission, we had to do something that you normally wouldn't do. Normally, you would do your reconnaissance. You would map the object, and you would pick out your landing sites, and you'd have a really good understanding of what you were landing in, and then you would send a lander. And in this case, we did it all in one mission. And so when we did our orbit insertion in August, we literally had like 2 months to figure this thing out, to figure out where the lander is going to go, because we're doing this all in one mission.
And
that's just incredibly risky.
That's amazing. I mean, congratulations really for the great work that you're all doing. And it's like 250 scientists in 11 countries. I mean, this is an incredible international mission. I'm holding right now this model of the comet with the 2 lobes, the inferior and superior lobes. They're a little rubber ducky. And it is my understanding that the landing site has been selected to be right on top of the ducky, on top of the head of the ducky. Is that true?
It's not exactly right on top. It's on one of the lobes, and we actually have an experiment called the concert experiment. If we put the lander down right on top, it's not optimum for the radio waves to pass through the whole body and go to the other side. It's kind of like an ultrasound.
I see.
And so we needed to be a little bit more towards the middle of the object in order for that experiment to have its best chance.
Okay, so it's not quite on top. It's a little bit offset. Yeah, because what Claudia is talking about is that the Philae lander has an antenna, but also the Rosetta mission has another antenna that's kind of like twins. And between the 2 antennas, they're going to be passing through radio waves through the comet to have an idea of the composition and whether it's layered, etc., the structure of it. And it's almost like doing a sonogram on the comet. So that's a very exciting experiment. Which other experiments?
I think that's one of the most exciting
One of the most exciting ones? Which other favorites do you have in terms of the experiments that Philae or Rosetta is doing?
That's one of my favorites because that allows us to see inside, to see if there's any homogeneous or not homogeneous pockets.
Great.
It's, you know, most of the time you're just dealing with the surface, and there's nothing that really gives us insight into what's inside. And for when I did my dissertation, we thought that the comet was like an Oreo cookie. Maybe it had the outside was this crusty, dark, porous material, and inside it was the icy stuff. And now it probably is not like that at all. So this is one of the experiments that's going to help us find out what the inside is like and if there's any layers or rubble, piles of rubble inside. So I'm looking forward to that.
Well, we have a very eager audience here, and I'm just wondering if anybody here has a question for Dr. Alexander that you would like to say. And in the meantime, I think I'm going to run the simulation of the landing itself so that you can just get a sense of what that's going to be like. But does anybody here have a question for Dr. Alexander? Yes.
So my question is, why this comet? I mean, why 67P?
Claudia, why this comet?
Okay, so as much as we'd like to say that we deliberately found this incredibly unusual target and we said that's got to be the one we go to target and look at, this is a complete accident. In the first place, when you plan a long mission and you're going to these travelers that are coming to you, we have a short list of maybe a dozen targets like that to plan to. So the same ones keep coming up. Temple 1, Schwarzmann-Walkman is another comet that a lot of missions plan to.
I see.
So you're going to something that you know is going to be there, and you know, and so it's more like, let's just get to the one we can go to.
That's
fantastic. And then in our case, the original comet we wanted to go to was called Virtanen, and we had a launch delay, and we had to pick a new target completely. And so we sort of, kind of closed our eyes and picked one that we could get to within the time limit of the mission.
It seems to me that you picked right because
it was an accident.
This is an amazing shape and amazing challenges, but I think that you have in here a lot of potentially new science and new questions. You know, did this form as two independent bodies? Is it something that got eroded, or do they have different ages, the two lobes? I mean, there's all sorts of really interesting questions. One more question before we wrap it up, because we're almost to the end. Anybody else? Yes, sir.
Hi. You're supposed to ask one dumb question every time, I know, but you're talking about a landing. This is actual people actually landing on this comet.
No people, just
this is
an
all done
unmanned
with photography.
spacecraft.
It's all
Just
done
instruments.
With instruments, okay. But how far away from where we are now is the comet?
How far away is the comet from here
From
right
here,
now?
yeah,
How
from
many
Earth.
astronomical units? How many? About 6 million kilometers, is that right? Claudia, how far is the comet from us?
It's about 3 AU right now, so that's about 300 million miles.
300 million miles. That's the distance. And it's going to get closer and closer to the sun. Okay, last one.
That's more like it in terms of distance.
Yep. Okay. Anything else? All right. Well, I really want to thank Dr. Alexandra. Let's all give her a very warm round of applause. She did a great job giving us the latest update. We want to wish you the very best. You know, Godspeed to you and the team, and we keep our fingers crossed for you. We're going to tune in on November 12th, 7:35 Pacific time in the morning. So watch your news. ABC is your official cover media sponsor, I believe. So watch TV, watch the internet, and we'll see your beautiful face there, smiling as you're doing now. Thank you so much, Claudia.
Hey,
Have a
thanks,
good night.
everybody. Good night.
So thank you so much. I really, on behalf of the Exploratorium, I also want to thank this amazing webcast team that behind the scenes here makes all of this possible. Thank you all for making it happen. Couldn't be done without you. I want to thank my Comet, who was so well behaved right here, you know, my little rubber ducky model, etc. So, and of course the audiences, you're wonderful, so interested, so eager. Thank you for supporting the Exploratorium. Let's keep learning about comets and tune in next week. We have another webcast right here on Thursday, the 13th of November at 7:30 p.m. with Paul Doherty, and he's going to give you all the latest after the landing of Philae. So come on back. See you then.